In this video, we're going to work an example problem related to calculating the amount of work done in a process. And so this is work done in the physics sense. So like force times distance, work done. Now it's important that as we do these problems, that you don't get bogged down with the physics of what's going on. So like, don't be so concerned with, well, what does work mean? The fact that you don't really understand what work means, don't worry about all that. This is all about illustrating how how calculus can be applied in a actual scenario in either physics or engineering, business, chemistry, biology. The authors of the textbook could have chosen any other topic outside of work, and it would have served the exact same purpose of what the calculus book is trying to teach us. So like if you're an expert in any of these fields, so like here it's a physics problem, but we're going to do in later sections, we'll do like problems in economics. If you're an expert in these fields, then they'll tell you that these problems that they give are really simple. And they're really simple because they know that the people that are learning calculus aren't experts in these fields, so they can't give these complex examples. But even though they're simple examples, it still does a great job of illustrating how the calculus is being applied, specifically here, the integration. And this here is a really good example of, I think this is a really good example of what the textbook is trying to teach us in this section, okay? And what they're trying to teach us is how you can take some sort of parameter that you want to calculate in business, whatever, physics, engineering, whatever, and you can think about calculating that parameter through the lens of integration. And you can clearly see like the delta x of the integral, the dx, that you can see like the actual meaning of that. You can see the meaning of the function. You can see how you can break down some system in business or engineering or whatever. You can break it down, verbally and even visually in terms of that infinite sum. It really makes it clear. So let's take a look at this and you'll see what I mean. It says when gas expands in a cylinder with radius r, the pressure at any given time is a function of the volume. So the pressure, we've got this piston cylinder and here's the chamber. The pressure in the chamber is a function of the volume, V, of the chamber. The force exerted by the gas on the piston is the product of the pressure and the cross-sectional area of the piston. So the piston radius is R, so this is R, okay? And so the force on the piston face is just the cross-sectional area of that piston times the pressure. That's how pressure works, all right? So it says, show that the work done by the gas when the volume expands from volume V1 to V2 is given by this. All right, so to give you a sense for this, when you take thermodynamics, and you're analyzing a piston cylinder, it's well known that the work done is, if let's say it's a constant pressure process, then the work done is just that constant pressure times delta V. So let me prove this to you first. And then with this, we'll clearly see where this formula comes from, and you'll see how integration, get a clear picture of how integration is applied to a real system. All right, so it's the work done to, because what they're talking about is like, you can imagine this is like has a resistance against it. Like you need to be able to push like in an internal combustion engine, right? To push the piston, there's a lot of resistance. You got to push the wheels. You got to turn the crankshaft. So it's a force over a distance. It's a lot of work. That's the whole point. So they're saying, so when the volume increases, so you go from V to delta V, an increase in volume, what's the work done? What's the force times the distance the piston moves? And this is a simple case of work because it's force times distance. The force is going to be in the same direction as the displacement of the piston. So you could just multiply the force times the distance. That's a nice thing about piston cylinders, is that the force on the piston face, since the piston face is perpendicular to like the direction that the piston can move, then the force and the piston and the direction of movement are going to be in the same direction. So you don't have to think about, well, the force is in this direction, but the piston's moving in this direction. So in that case, calculating work is a little bit different. But here, we don't have to think of, that's not a complication. So, all right, but if the pressure is constant and you have a change in volume, You go from V to delta V at constant pressure. Then you just multiply that constant pressure times the change in volume, and that's the work done. Let's prove this first. So the force on the piston face due to the pressure we see here is pi r squared P. Yeah, you take the cross-sectional area of the piston that's exposed to the pressure and multiply that times the pressure. That's like the definition of pressure if you want to convert pressure to force on an area. So P is pi r squared, or no, we want to get F. Yeah, so pi r squared P, that's the force. And then times the distance. What's the distance? When you go from V to delta V, what happens? It's the distance is delta X. You're going from X to delta X. Right, and we're assuming we're just doing like positive work here, so they're not talking. You could have negative work if the piston pushes in, but we're just thinking about an increase in volume. Okay, so that's the force times the distance, right? That's the work done. Whenever you increase the volume, this is the work done. This is the force times the distance. The force is in this direction. The piston moves in that exact same direction as the force, so you just multiply the force times the distance moved. Okay, now, if we rearrange this, let's bring the delta X here. Okay, what is this? Pi r squared delta X. This is the delta V. You see? So look, this is P delta V. There you go. So I've proven to you that if there's in a piston cylinder, if there's a volume expansion or contraction at constant pressure, then the work done on the piston is P times delta V. Okay, so now we can use this to prove this formula. And this is the main concept here of this video. This is the important part. Because, okay, the integration process, the infinite sum process, what's the essence of what we're doing with an infinite sum? So if we look at this integral here, the independent variable is dv. We've broken up into these these delta V pieces, right? And then here's the function within the integral. The big idea, one of the big ideas when it comes to this infinite sum process is that we're assuming like the height of the rectangle is constant over each interval. That's like one of the main things that we do in integration. Like for any integration, you can think about the idea of a rectangle. Even if you're not calculating areas under curves, you can always think about the idea of a rectangle because you're multiplying this constant interval width, delta V or dV here, times it's a constant height. It's this function evaluated at some position within the interval, and then that's going to be the constant height of the rectangle. Okay, so now if we think about that from like a more physical reality standpoint, we know that the work done in a piston cylinder, if you're writing it in terms of pressure and volume, okay, is if the process is at constant pressure, then it's P delta V. Well, we don't have a constant pressure process here. This P is not constant here. Okay. However, from an integration standpoint, we can think about the idea of that if we make the delta V's very small. So over, this went from X to X plus delta X. As it's going from X to X plus delta X, if we make those changes in volumes, those corresponding changes in volumes, if we break it down into that process down into pieces, and the delta V's are really small, then we can assume for each little delta V, the pressure is constant. That's what we're going to do. If the delta V's get small enough, the little delta V pieces we break it up, the process up into, get small enough, then it's a good assumption to say that the pressure is constant. Well, in that case, we can calculate the work done. It's P delta, it's that constant pressure times that delta V. And then we can add it, so we can just, for every little tiny interval, we can assume these constant pressures and then add all of those up. And then we'll get the actual work done. And so you see the big idea here, the idea of how it's a really clear illustration of, we're not thinking really about rectangles anymore. You are, if you did the PV curve, the pressure volume curve, this is actually, if you're going from A to B, the work done is the area under the pressure volume curve for sure. That's true. Okay. But just the big point here is you're thinking about how since we know that P, a constant pressure process, is you can calculate the work done just P delta V. It's this idea of we're breaking it down into these constant pressure processes. I'm trying to do the best I can to illustrate how we're really describing this process here, this process in physics. We're really describing the integral. We're describing each. We're breaking down the non-constant pressure process into constant pressure processes, and then summing all of those, summing the work done for each of those constant pressure processes to get the total work done for the non-constant pressure process. You see how that we're describing the concept of integration, but from the angle of the actual of a system in physics. And you could do the same idea with anything in any other subject. Okay. And so you see, if you go from V1 to V2, you're going to have these little delta V's all the way from V1 to V2. As n goes to infinity, those delta V's are going to get really small. And so the idea of, okay, I have a constant pressure in each of these delta V's, that's going to be a really good assumption. So this is going to converge to that. The integral as n goes to infinity, as the delta V's get tiny, well, then this is going to be equal to the work done. This is like the definition of work done for a non-constant pressure process. So, let me go through it. So the idea is you got the pressure as a function of the volume. We're going from V1 to V2. We're going to break this up into a certain, like n pieces. Let me just put 1, 2, 3, 4, 5 pieces, let's say, but it could be any amount of pieces. The width of each piece is going to be the same. It's going to be a delta V, and that would be equal to V2 minus V1 divided by the number of pieces we choose. That's going to be the delta V, right? So we're going from V1 to, it's the entire expansion process. We're going from V1 to V2. We're going to break that up into these little intervals, these delta X or delta V intervals. Kind of the same idea. Each delta X is like a little delta V. For each of the delta V's, we're going to assume the pressure is constant. Even if we were just breaking it up into 10 pieces, that's still what we do. So we're going to assume a constant pressure. That's not the best example. Let me use like here. We're going to assume a constant pressure. You can see, there's a little bit of error there, right? It's because it's not necessarily constant. For that delta V, we're going to assume a constant pressure. And therefore, the work done for that delta V is for like the ith delta V. So we're going to have I, we're going from I is equal to 1 to whatever n is. The work done for the ith interval is the P, which is what? It's the P evaluated at VI star, right? This pressure is a function of volume. The star means we can choose any point we want within the rectangle, within the interval. So it's that P and then times the delta V, which is this. Okay? So now the work done in the process is approximately equal to the sum from I is equal to 1 to the n that we choose of P VI star delta V, right? This is not the work done. This is the work done in the ith subinterval. But now when we want to sum all those intervals up over from V1 to V2 to get in here it would be an approximation for the work done in the process. However, we can get the actual work done when we take the limit as n goes to infinity of this. This is the Riemann sum. As n goes to infinity, what happens? Well, here there's only one factor to consider, and that's the fact that that assumption of a constant pressure, it's not an issue anymore. You might say, well, how is that not an issue? It's not an issue in the exact same way that the area under the curve, so that's the idea with the area under the curve. You're assuming that the function is constant at every interval when it's obviously not. It's curvy, but as n goes to infinity, it converges to the exact area. So really the idea here is that the exact work done in this process is the area under this curve. And we know that we can calculate the exact area under the curve. So that's how we know that assumption of a constant pressure it's the error goes away. And so now we can turn this into an integral, this infinite, the limit as n goes to infinity is I is equal to 1 to n. That's the elongated s. We're going from v1 to v2. Now, as n goes to infinity, we don't need vi star anymore because we could choose any point we want, the left endpoint, the right endpoint, whatever, and they all converge to the same value as n goes to infinity. So we just put p. P of v. You don't have to put the of v, just like this. Okay? Now, as n goes to infinity, delta v gets infinitesimally small, so we put dv. And there you go. The work is equal to, there's the formula.